All right, so one of the things I'm doing now, and again, please feel free to give your feedback. I'm thinking of probably writing more in class rather than just bringing stuff written. I don't know if that helps or not. When I have to write, it forces me to slow down a little bit. You may find that helpful. If you prefer, I can also write it before class and bring it. So I'll leave it up to you. I think in the last two recorded lectures, I wrote during the class. Anyway, you can let me know what you prefer. Okay, so the next thing I want to talk about is something called modes of convergence. All right, and this has to do with the different senses in which a sequence of functions can converge to a limit. Okay, so let's start with a simple example. All right, so I'm working in a measure space. Okay, so the definitions we're going to make are going to be for a measure space. So of course, if they hold in a measure space, they hold in a probability space. But before we make any formal definition, let's play around with some examples so that we get a little intuition about the definitions we're going to make in 5 minutes. Okay, so let's start with a simple case where our measure space is the following. The underlying set omega is the open interval 0, 1. The sigma algebra is the Borel sigma algebra on 0, 1. In other words, it's the smallest sigma algebra containing all the open intervals. And let mu be Lebesgue measure on 0, 1. So basically, mu is just your traditional notion of length on 0, 1. In other words, if somebody gives you an interval, mu of that set is just the difference of the endpoints. Okay, now consider this sequence of functions, f1, f2, f3, and so on. This sequence of functions is much easier to write down than to, it's easiest to probably draw this and describe it to you in words as to what's going on. So what's going on? I'm taking the interval from 0 to 1 and I'm splitting it into two pieces. So f1 is 1 on the first part, 0 on the second part. f2 is 0 on the first part and 1 on the second part. Then I'm taking the interval from 0 to 1 and I'm splitting it into 4 pieces, 4 equal pieces. Then f3 is 1 on the first part and 0 everywhere else. f4 is 1 on the second part, 0 everywhere else. f5 is 1 on the third part, 0 everywhere else. f6 is 1 on the fourth part, 0 everywhere else. So far, so good. Then I'm going to take the interval from 0 to 1 and I'm going to split it into 8 equal pieces. Then f7 is 1 on the first part, 0 everywhere else. f8 is 1 on the second part, 0 everywhere else. There will be 6 more like this. Once I'm done with that, I will take the interval from 0 to 1 and I'll split it into 16 parts. Then I will split it into 32 parts, then into 64 parts, and so on. Does everyone see how the sequence is going? If I give you the sequence and I ask you to draw the next 10 terms, do you think if you have 5 minutes, you can do it? Is the idea clear what's going on? We're first taking the interval, breaking it into 2 pieces. Then we're taking the interval, breaking it into 4 pieces. Then we're taking the interval, breaking it into 8 pieces, and so on. Okay. Now let's ask the following question. You get the sequence of functions. Let's ask this question. Does the sequence of fn's converge at any x in 0, 1? What do you guys think? Does it converge at any x? Pointwise. If I fix an x and I ask you, does the sequence converge at x, what would you say? Dhiren, Maheshwari? Suman Kumar, does the sequence converge at any x in 0, 1? So fix an x, does the sequence converge at x?
If our x is finite, then I think it must converge.
No, I disagree. It will not converge. So what is going on here? Take any x you like. Let's say you take x equals, for simplicity, let's say you take x equals 1/4, right? Then here the function will be 1 at a quarter, then it will be 0. The point is that as you go on the sequence, there will be infinitely often the function will be 1 at that point, infinitely often it will be 0 at the point. If you think about this, basically this little bar is moving all over the place. So no matter what x you pick, the bar is going to at some point be above it. So the value of the function will be 1. And the bar is then going to move. So the value of the function is going to be 0. then the bar is going to get smaller. And then again, at some point, it's going to come above the point you have chosen, and then it's going to move. So no, this function does not converge pointwise anywhere on 0, 1. Okay. It does not converge anywhere because take any x in 0, 1. You know what I mean by the bar, right? This is the bar. Right, in the first two cases, the bar is of length 1/2, and it's there, moves. Then the bar becomes of length 1/4, 1, 2, 3, 4. Then the bar becomes of length 1/8, 1, 2, 3, 4, 5, 6, 7, 8. So no matter which point you're at some point the bar will be above you and the value of the function will be 1. But then the bar will move, the value of the function will be 0. So infinitely often, take any point you like, infinitely often the value of the function will be 1, the value of the function will be 0. So no, this sequence of function does not converge anywhere on 0, 1. Now let's ask a different question. Let's fix an epsilon in 0, 1. Okay? So if you want to think epsilon equals 1/2. And now let me ask you this question. As n gets large, what happens to the measure of the set of all omega and omega when mod f of omega is greater than epsilon? What happens to this set? So what is this set? This is the set of all points in 0, 1 where the value of the function is bigger than epsilon. What happens to the size of this set? It keeps shrinking, right? The size of the set keeps getting smaller. The set moves around all over the place. In the first picture, this set is here. In the second picture, this set is here. Okay, so basically just think. For concreteness, think epsilon equals 1/2, okay, for instance. So in the first picture, the set of points where the function is bigger, absolute value of the function is bigger than 1/2 is this set right here. In the second picture, the set of points where the value of the function is bigger than 1/2 is here. In the third set, it is there. In the fourth function, it is there. Fifth function, it's here, and so on. So the set where the value of the function is greater than 1/2 in absolute value moves around. But as you go further and further into the sequence, that set gets smaller and smaller. Okay, so this is the set of all points omega and omega where absolute value of f of omega is bigger than epsilon. This set moves, it does not stay fixed, it's all over the place. But as n gets larger, its size goes to 0. Okay, so this is another way in which you could say that the function is going to 0. And this is what we will call convergence in measure. We will say that this sequence of functions converges to 0 in measure. What does that mean? That means that if you look at the set where the function differs from 0 by some amount, as n gets larger, that set gets smaller and smaller in measure. It may move around. Nobody's saying it's staying fixed. It may move around, but it's getting smaller and smaller. Okay, so let's just make a note here. As n gets large, what happens to measure of the set of all omega and omega such that absolute value of f omega greater than epsilon? This goes to 0. Okay, so this is going to motivate the next definition we're going to make. We're going to define something called convergence in measure. We already have talked about convergence almost everywhere, or almost surely, but this convergence in measure is perhaps new. So the heading here is types of convergence. All right, let omega f mu be a measure space. All right, so in particular, you could be talking of a probability space. Okay. Let Fn and f be measurable functions from omega to r. Okay, so I have a sequence Fn of measurable functions taking omega to r, and I have a function f taking omega to r. So basically, we're going to talk about different senses in which Fn converges to f. So here's the first sense in which Fn can converge to f. By the way, before I go any further, you can talk about Fn converging to f pointwise. Right? Naturally, you can do that, right? And You could also talk about uniform convergence, right? That you've already studied in basic analysis in BSc. So of course, those notions are still there. You could talk about what does it mean for Fn to converge to F pointwise. You could talk about what it means for Fn to converge to F uniformly. Those two you already know, but now we're adding to the list. And remember, to talk about Fn converging to F pointwise, you do not need a measure, you do not need a metric, nothing, right? Because you're talking of real valued functions. Similarly, to talk about Fn converging to F uniformly, you do not need any other structure on the domain, right? If you go back and look in your analysis books from your BSc, you will probably see this. Suppose I just have a set S and I'm not putting any structure on it. I'm not saying you can add things. I'm not saying you can measure distances. I'm not saying there's a topology, nothing. I just have a set S and I have a function Fn taking S to R and I have a function F taking S to R. I can talk about what it means for Fn to converge to F pointwise. I don't need any structure on S. Similarly, I can talk about what it means for Fn to converge to F uniformly. I don't need any structure on S. Now, if I have additional structure on S, such as I have a measure, then I can talk about weaker senses in which convergence is happening, and that's exactly what we're doing here. So we'll say that Fn converges to F almost everywhere. This is AE. You know what this means? Fn converges to F almost everywhere means you can take a set of measures, throw it away, and on whatever is left, you have pointwise convergence. So if there exists a null set N in F, such that when you throw away N, you have pointwise convergence. There's a null set N in F such that for all omega in omega, take away N, we have Fn omega converges to F of omega as M goes to infinity. All right. So that's what we mean by almost everywhere convergence. By the way, you will have seen this in your real analysis courses. Sometimes if you want to emphasize which measure it is you're talking about, you may say mu almost everywhere. Okay, and this is particularly of use if there is more than one measure that you're working with. Right? Suppose you're working with the measure mu, measure nu, the measure lambda, and you want to say that Fn converges to F almost everywhere, then you need to specify almost everywhere with respect to which measure. So in that case, if it's with respect to lambda, then you may say lambda almost everywhere. Okay, so that's what this is about. But when you have only one measure in town, there's no need to make all these extra specifications. All right, so that is what it means for Fn to converge to F almost everywhere. The next thing I want to define is what I mean by convergence in measure. Two. So say that Fn converges to F in measure if for every epsilon greater than 0. So here's what I'm going to say. I'm going to say fix an epsilon greater than 0. Look at this set omega and omega, where absolute value of Fn of omega minus F of omega is greater than epsilon. Okay, so I'm going to say fix epsilon greater than 0 and look at this set. What is this set? This is the set of all points omega and omega, where Fn omega minus F omega in absolute value is greater than epsilon. So you can think of this as your bad set, so to speak, right? Because on this set, the difference between Fn and F is bigger than epsilon. Convergence in measure is saying that this set is allowed to move around. It can go wherever it likes, but it should get smaller and smaller as n goes to infinity. So convergence in measure is going to say that the measure of this set mu should go to 0 as n goes to infinity. All right, so say that Fn converges to F in measure if for every epsilon greater than 0, the measure of the set of all omega in omega such that absolute value of Fn omega minus F omega greater than epsilon goes to 0 as n goes to infinity. All right, and let's talk about a third sense in which Fn can converge to F. So we have kind of said this informally, right? We said that suppose we are working on a measure space omega F mu. Okay, and I have a function x taking omega to r, right? Suppose x is integrable, right? Then we have said that x is an L1, okay? Now what you can do is, and again, there's this whole theory of LP spaces. If integral absolute value of x to the p d mu is finite, then you can say that x is an LP. So if you're wondering in the next definition where these terms come from, that's where it comes from. Okay, so the third sense is the following. So if integral absolute value of Fn to the p is finite. Now, by the way, there's only one measure in town, so I'm not specifying which measure. Okay? If integral absolute value of f to the p is finite. Okay, so here 1 less than or equal to p less than infinity, we say that Fn converges to f in LP. This happens if integral absolute value of Fn minus f to the p goes to 0 as n goes to infinity. Okay, now the idea is that to talk about convergence in LP, I'm going to take the difference between Fn and f, take the absolute value and take the p power. Now I need to be sure that that is integrable. Right, so for that to happen, it is sufficient to assume that integral absolute value of Fn to the p is finite, integral absolute value of f to the p is finite. Okay. So that's what we mean by convergence in LP. So let's just once again talk about analysis and probability and what the names are in the different cases. Okay. Okay, so this is basically your dictionary, right? You have seen this before. Measurable functions in real analysis are random variables and probability. Integrals become expectations and so on. Okay. So here, let's add to our dictionary here. So this is convergence almost everywhere. In analysis is called convergence almost surely in probability. This I'm pretty sure we have already talked about. Again, if you want to specify which probability measure you're talking about, you could say P almost surely, okay, if the need arises. Then the other thing is convergence in measure. This is called convergence in probability. Okay, so no need to give you these definitions. All you need to know is this dictionary to translate terms from one language to another. Okay. All right, so now what I'll do is here I'll work in a measure space because everything I then say will carry over to a probability space. Okay, so now the next thing I want to do is I want to talk about the relationship between these notions of convergence. So before I start writing, let me just tell you what's going to happen. By the way, if you guys are on campus, I suspect many of you are. Can I request you to keep your videos on, please? If you can at home, that's fine. But if somebody's at home, I'm not going to bother you. But if you're on campus, I think it's fair to ask. Okay. All right. So now before I actually go ahead and prove the relation, let me just tell you what's going to happen. We will say that suppose Fn converges to F almost everywhere. If your measure space is finite, then you will have convergence in measure. Okay. Suppose Fn converges to F in measure. And regardless of what measure space you're working on, there will be a subsequence which converges to F almost everywhere. A third thing is if Fn converges to F in LP, then that is going to imply convergence in measure. So let's see how all this works. All right, so here's our proposition. All right, notation is as before. I'm not going to repeat the whole thing. So the first claim is suppose mu of omega is less than infinity. if Fn converges to F almost everywhere, then Fn converges to F in measure. All right, that means this is always going to happen in a probability space. In a probability space, convergence almost surely will definitely imply convergence in probability. Second, if Fn converges to F in measure, then you can find a subsequence of Fn which converges to F almost surely. Then there is a subsequence Fnk such that Fnk converges to F mu almost everywhere. Third claim is, so suppose integral absolute value of Fn to the p is finite. Integral absolute value of f to the p is finite. So suppose this is the case for some p. Our claim now is that if Fn converges to F in Lp, then Fn converges to F in measure. Okay, so before I go any further, I just want to ask you really quickly. Look at the picture we started with. Can somebody give me which subsequence will work here? Okay, let me go back here. Any questions with what I'm saying here, in particular with point number 2? Any questions? Okay, I'm going to take that as a no, you understand what that means. Let's come back to the picture we started with. I claim that in this case, Fn converges to 0 in measure. And now I'm asking you, give me a subsequence which converges to 0 almost everywhere. What would you say? Anyone? Sanjukta? Is the question clear?
Sir. Yes, sir. Sir, the subsequence can be, I mean, f of that index will be some n into 2 to the power k. I mean, for large k, it is becoming smaller and smaller. So almost surely will be there. Okay. You're thinking much
In a much more detailed way than I am. I was just thinking in terms of the picture. Can you tell me the first view? I'm not saying what you're saying is correct or incorrect. I'll have to think about it. But I was just saying, looking at the picture, can you tell me what subsequence might work? So how about suppose I take F1,
F3.
then I take F3,
F7.
then I take F7.
Yes.
And then let's see. Okay, so F6, add 8 to that 14, then F15, and so on. Does that make sense? So I'm taking the function where the bar is absolutely to the left. Now you may say, why am I doing that? Why am I discriminating? Why not take it when the bar is to the right? You can do that also. You could take F2, and then you could take F6, and then you could take, I think it would be F14, and so on. Okay. So just think about it. Make sure you can identify a subsequence from here. If you can write down a formula, that's great. But at least if you can tell from the picture how you can pull out a subsequence which will converge to 0 almost everywhere, that could be helpful. Okay. So that was that. That was just returning to that example we did. Now let's prove this. All right, so here's the proof. So suppose mu of omega is less than infinity. Okay, right. So that is needed for proving part 1, and that Fn converges to F mu almost everywhere. Okay, so suppose this is true. We want to show convergence in measure. Right, so let epsilon greater than 0 be given. Right, we want to show that mu of the set of all omega in omega such that absolute value of fn omega minus f omega greater than epsilon goes to 0 as n goes to infinity. And we're just setting up the problem here. This is what we have to do. So let's see how you do that. So first of all, let's name a few sets. So let an be the set of all omega in omega such that absolute value of fn omega minus f omega greater than epsilon, right? And what do we want to do? We want to show mu of an goes to 0. Okay, now we are told that fn converges to f almost everywhere. That means if you throw away a null set, on whatever is left, you have pointwise convergence. So let n in f be a null set such that for omega in omega minus n, we have fn of omega converges to f of omega. And now this was possible by assumption. We were told at the beginning that there is a null set such that if you throw it away, on whatever is left, you have pointwise convergence. So let n be such a null set, throw it away. Okay, let me do the following. Let b equals omega minus n. Okay, so what can you be sure of? Then b is a measurable set, right? Because n is a measurable set, you threw it away, you took omega minus n, that is measurable. And you also know that measure of omega minus b is 0. With measure of omega minus b is 0. Okay. All right. Now here's what we'll do. So if omega is in b, right, then absolute value of fn omega minus f omega is less than or equal to epsilon for n large enough. Okay, so what am I saying here? Suppose omega is in B. Now remember, on the set B, fn converges to f pointwise. So omega is in B. On the set B, fn converges to f pointwise. So if somebody gives me an epsilon for n large enough, absolute value of fn omega minus f omega will definitely be less than or equal to epsilon. Why is this going to be the case? Because for this omega, fn is converging to f. Okay, so since this is true, right? So what's another way of saying this? So I'm saying suppose omega is in B, then absolute value fn omega minus f omega has to be less than or equal to epsilon for n large enough. Do you agree that I am saying that omega will not belong to an for n large enough? Okay. Or for omega in B, absolute value of fn omega minus f of omega must be less than or equal to epsilon for n large enough. Which means for omega in B, omega must fail to make it into an for n large enough. So for n large enough, omega should be missing from an. Any questions with that? i.e., omega is missing from an for n large enough. Another way to say that is the following. if I take the indicator function of an and evaluate it at omega, this is going to be 0 for n large enough. Yet another conclusion you can draw is, i.e., indicator an of omega goes to 0 as n goes to infinity. Right? Okay, now note that just if you pay attention, this statement, which I'm marking in square brackets, is stronger than this statement in curly brackets. Okay. The statement in square brackets, indicator an omega is 0 for n large enough. This is stronger than the statement in curly brackets, which just says indicator an omega goes to 0. But anyway, this is all we need. Okay. Actually, they're equivalent. Wait. They're perhaps equivalent because this function can only take the values 0 and 1. So they're probably equivalent. But in any case, this is all we need. Okay, so what you get is thus, what you get is indicator an. Okay, let me rewrite that. Thus, for omega in B, indicator an of omega goes to 0. But remember, B has full measure. In other words, B complement has 0 measure. So what we're saying is that indicator an goes to 0 almost everywhere. The indicator an goes to 0, mu almost everywhere. You guys with me? Now I want to use dominated convergence theorem. Right? Remember, if I want mu of an, that is the same as the integral indicator an d mu. Okay, so it makes sense. And remember, we want to show that mu of an goes to 0. That's what we want to show. In other words, we want to show that these integrals go to 0. So it makes sense to bring in the dominated convergence theorem. I'll say the function indicator an goes to 0 mu almost everywhere. So now if I can bring in dominated convergence theorem, I can conclude that integral of indicator an d mu converges to 0. And if I do that, then my job is done. So now I need a dominating function. Can anybody suggest a dominating function? I'm giving you a hint. This is where you're going to use the assumption that the measure of the whole space is finite. Suppose I take the function 1. It's going to dominate, that's no problem. But remember, the dominating function has to be integrable, right? And a constant non-zero function is going to be integrable if and only if the measure is finite. Okay, so that's where we're going to use 1 as our dominating function. If you want, you can use 2 also. There's no harm in that. But the point is that we need the measure to be finite. All right. So if you're wondering why these assumptions were there on mu of omega being finite, here it is. Okay. This indicator an goes to 0 mu almost everywhere. Now we want to use dominated convergence theorem. So now you'll say, now indicator an, an absolute value is less than or equal to 1. Then since mu is finite, so here's where we're using finiteness of the measure. Since mu is finite, 1 is integrable. All right, and so now you can use Lebesgue dominated convergence theorem. The Lebesgue dominated convergence theorem, mu of an, which remember is just the integral indicator an d mu. This thing goes to 0 as n goes to infinity, and so we're done. Any questions? Okay, so this proves that on a finite measure space, okay, let me put it another way. If you have almost everywhere convergence, to make the leap from there to convergence and measure, it is sufficient that the measure of the whole space be finite. Does anybody think it is necessary for the measure of the whole space to be finite? I'm just asking you to make a guess. Hopefully you'll guess right. Is my question clear? If Fn converges to F almost everywhere, clearly it is sufficient. Okay, Fn converges to F almost everywhere. I want to conclude convergence in measure. If mu of omega is finite, that is sufficient. Now my question is mu of omega finite necessary? I don't think so. I'm sure you can come up with examples where it, yeah, so I don't think mu omega is necessary by any means. It's just sufficient condition to transition from almost everywhere to convergence in measure. Questions? All right, so now let's prove the second part. The second part is to show that convergence in measure implies convergence. Convergence in measure implies convergence almost everywhere along a subsequence. So let's prove that. All right, so now this is part 2. So suppose Fn converges to F in measure. All right, now I need to come up with the subsequence, right? So it'll be helpful to write out the first few terms of the subsequence, and then we will just give the algorithm for recursively getting the terms of the subsequence. So why not start with let n1 equals 1? Okay, so basically we're trying to get the subsequence f n k. So basically I need to tell you how to get this nk. That's what I need to tell you. And then of course, once I tell you how to get the nk, we need to check that everything works. So but when you see this n1 equals 1 and you're wondering what is that? Well, the point is n1, n2, n3 and so on are going to tell us which terms of the subsequence we're going to pick. Okay. So let n1 be 1, and then I'm going to pick n2 as follows. So choose n2 greater than n1 such that mu of omega in omega such that absolute value of fn2 of omega minus f of omega greater than a half is less than or equal to 2 to the minus 2. This is of course 1 over 2 squared. Right, I can do this, right? Because what does convergence in measure mean? Convergence in measure means that for any epsilon, in this case a half, if you go far enough into the sequence, then the measure of the set where the terms of the sequence differ from f by more than epsilon can be made arbitrarily small. In other words, it can be made smaller than 1 over 2 squared. So far, so good. Now I'll continue this. So now I'll say choose n3 greater than n2 such that mu of the set of all omega and omega such that absolute value of f and 3 of omega minus f omega greater than a third is less than or equal to 2 to the minus 3, which is 1 over 2 cubed. Again, you can do this because of convergence in measure. Convergence in measure says that for any given epsilon, if you go far enough into the sequence, then the measure of this set can be made arbitrarily small. In other words, it can be made smaller than 2 to the minus 3, and you'll continue in this fashion. So the general algorithm is this. So in general, choose nk greater than nk minus 1 such that the measure of the set of all omega in omega such that absolute value of f n k of omega minus f of omega greater than 1 over k is less than or equal to 2 to the minus k. You guys with me so far? I think you will agree that we have at least got a subsequence. Now, whether it has the desired properties or not is another story, but we certainly have a subsequence. This gives us a subsequence f and k going from 1 to infinity. All right, now I claim that this subsequence has the desired property. So we claim that f and k converges to f almost everywhere as k goes to infinity. All right, so let's prove this. So let's do the following. So let ak be the set of all omega in omega such that absolute value of f n k of omega minus f omega greater than 1 over k. Remember, these are precisely the sets that we were talking about up here. All right, so what do we know? We know that mu of ak is less than or equal to 2 to the minus k. Now, I looked up the Borel-Cantelli lemma, and it seems that only 5 of you or so, at least when we started the lecture, at least only 5 of you have watched the video. Now, I'm going to assume that you have watched it because it has been uploaded. So I'm just going to use the Borel-Cantelli lemma here. If you haven't watched it, you can go fill in the holes. Or you may have learned it in a different course also. In any case, I'm going to use the Borel-Cantelli lemma. In the video on Borel-Cantelli lemma, the Borel-Cantelli lemma has 2 parts, part 1 and part 2. It's stated for a probability space. The first part can be generalized to a measure space. The second part talks about independence, so there's no analog in measure spaces. But anyway, so I'm going to use the Borel-Cantelli lemma now. We know that mu an less than or equal to 2 to the minus k. No, not mu of an. Sorry, there's a mistake here, guys. Just hold on. Mu of ak. Mu of ak less than or equal to 2 to the minus k. So I have 0 less than or equal to mu of ak less than or equal to 2 to the minus k. So I'll have 0 less than or equal to sum k going from 1 to infinity mu of ak less than or equal to sum k going from 1 to infinity 2 to the minus k, which is 1 less than infinity. Okay, so now what I have is I have a sequence of measurable sets such that if I take all the measures and I add it up, I get something finite. So I can use the Borel-Cantelli lemma. So by Borel-Cantelli, 1. So once again, the Borel-Cantelli lemma in the lecture has been stated for probability measures. So there's part 1, part 2. Part 1 also works for just measures. It doesn't have to be a probability measure. By Borel-Cantelli lemma 1, we have mu of lim sup of an is 0. Okay, now I claim that this will give us what we want. Now here, lim sup of an. So lim sup is inf sup, so it's intersection union. Okay, so this is intersection n going from 1 to infinity union k going from n to infinity ak. All right. So let's do the following. Let n be this set lim sup an, which of course by definition is intersection n going from 1 to infinity union k going from n to infinity ak. Now I claim, okay, so first of all, note that mu n is 0. Okay, that is just obvious. If you believe the Borel-Cantelli lemma part, you know mu of lim sup an is 0. And now I'm just giving it a name. I'm calling this lim sup of an n. So mu of n is 0. To complete the proof, I should convince you that outside of n, you have pointwise convergence. So now I need to show that outside of n, I have pointwise convergence. So we claim that if omega is in omega minus n, then fnk of omega converges to f of omega. So let's see why this is true. So indeed, suppose omega belongs to omega minus n. Okay, so what am I saying? I'm basically saying that omega is missing from n. In other words, omega is missing from this intersection. Now, if omega is missing from the intersection, it must be missing from at least one of the terms in the intersection. Right? Okay. Indeed, suppose omega and omega minus n, then there exists n greater than or equal to 1 such that omega is missing from union k going from n to infinity ak. Such that omega is missing and omega is not in the union k going from n to infinity ak. Now, if omega is not making it into a union, it must not be making it into any of the sets in the union. Okay. I.e., there exists n greater than or equal to 1 such that for all k greater than or equal to n, we have omega not in ak. Do you guys agree with that? All right, now let's remind ourselves what belonging to ak means. So thus, there exists n greater than or equal to 1 such that for all k greater than or equal to n, omega is missing from ak. So how do you get membership in ak? You get membership in ak if fn k omega minus f of omega is greater than 1 over k. So if you don't have membership in ak, that means this difference must be less than or equal to 1 over k. We have absolute value of f n k omega minus f of omega less than or equal to 1 over k. Okay. All right, so what this is saying is f n k omega converges to f omega as k goes to infinity. Right? But because what are you saying? You're saying that there exists n greater. So suppose omega is not in ak. I mean, no, suppose omega is not in this set. That means there is some n greater than or equal to 1 such that for all k greater than or equal to n, f n k omega minus f omega is less than or equal to 1 over k. That means n is how far you go into the sequence. After that point, all the functions are very well behaved with respect to the limit. In other words, all the functions, or rather this function fnk, is within a distance of 1 over k of the limit. In other words, as k goes to infinity, fnk omega converges to f omega. So in other words, fnk omega converges to f omega, and this is exactly what we wanted to show. Any questions with that? So here note that we have not made any use of finiteness of any measure space. Okay, so this holds regardless. Okay, so now let's prove the third part. The third part, let's see what does the third part say. The third part says, suppose that mod fn to the p is integral is finite. Suppose mod f to the p is integral is finite. And if fn converges to fn LP, then you can be sure that fn converges to fn measure. So let's see why this is true. Okay, so now let me just copy this sentence. And it'll be difficult, never mind. So suppose integral mod fn to the p is finite. Integral mod f to the p is finite. And that integral mod fn minus f to the p goes to 0. Okay, so assume this is true. For some 1 less than or equal to p less than infinity. Okay. So now here's what we're going to do. Okay, so suppose integral mod f to the integral mod fn to the p is finite, integral mod f to the p is finite, and integral mod fn minus f to the p goes to 0. And this is for some 1 less than or equal to p less than infinity. Okay, so now what do I want to show? I want to show that fn converges to fn measure. So this is actually written a little clumsy, in a clumsy way. So let me just do the following. Okay. Okay, now I feel better. This seems a little less awkward. So suppose integral mod fn to the p is finite, integral mod f to the p is finite for some 1 less than or equal to p less than infinity. Okay. Now what do we want to show? They're saying suppose integral mod fn minus f to the p goes to 0. We want to show that fn converges to fn measure. Right? So let epsilon greater than 0 be given. Right? So now here's what I'm going to do. I'm going to say note that mod fn minus f to the p is greater than or equal to mod fn minus f to the p, indicator fn minus f greater than epsilon. I think you will agree with this, right? Basically what I'm saying is mod x is greater than or equal to mod x, indicator mod x greater than or equal to alpha. That's all I'm saying. All right, that's, if you unwrap it, that's all I'm really saying. Right, mod x is greater than or equal to mod x times indicator of any set. In particular, the set here is the set where mod x is greater than or equal to alpha. Okay, well, okay. This also works. Mod x greater than alpha. That's all I've done. And basically, I'm saying a non-negative function is greater than or equal to the non-negative function multiplied by the indicator of any set. That's what I'm using. All right, and now I know monotonicity for integration for non-negative functions. So the integral of this has to be greater than or equal to integral of this, right? Okay. So here's what I'm going to get. So integral mod fn minus f to the p is going to be greater than or equal to integral mod fn minus f to the p, indicator absolute value of fn minus f greater than epsilon. You guys agree with that? Now remember that on this set, I can bound this from below by epsilon to the p, right? I'm on the set where mod fn minus f is greater than epsilon. In other words, on this set, so here's a true statement. Mod fn minus f to the p is greater than epsilon to the p. This is a false statement. This may not be true. But as soon as I put this indicator here, this is a true statement. Okay. So that's what I'm using here. So this is greater than or equal to integral epsilon to the p, indicator mod fn minus f greater than epsilon. And of course, you know what this is going to be. This is going to be epsilon to the p mu of the set where abs of fn minus f to the p is greater than epsilon. Remember, this is shorthand for something, right? This is just shorthand for mu of set of all omega in omega such that absolute value of fn omega minus f omega to the p greater than epsilon. All right, so what are you going to get? Now just focus on this is greater than or equal to this. Okay, forget about everything in between. Just divide by epsilon to the p. So mu of absolute value of fn minus f to the p Oh, no. Okay. I've made a mistake here. Sorry. There is a small mistake. Can somebody tell me what that is? There should not be a pth power there. Okay. Earlier I had put a pth power here. That should not be there. If it's there, then I should put epsilon to the p. Okay. So mu of mod fn minus f greater than epsilon is going to be less than or equal to 1 over epsilon to the p integral mod fn minus f to the p. And now remember here, epsilon is given to you. Somebody gives you an epsilon. But soon as they give you that epsilon is fixed. Right? So this 1 over epsilon to the p is fixed. Somebody has given you an epsilon, so that part is fixed. And this guy goes to 0. Why does it go to 0? By assumption. And so this goes to 0. And so mu of mod fn minus f greater than epsilon does go to 0 as n goes to infinity. And this proves that fn converges to f in measure. Any questions with this? All right. So one of the things I'm thinking of, I think that at about 1 hour, people kind of reach saturation point. So I'm thinking that rather than going on, I will probably record some material and share that with you, rather than going for another half hour. At least I know when I'm sitting in a class, my concentration starts to fade after 40-45 minutes. So maybe I'll stop right here. We do need to discuss a couple of things. Let me just stop the recording first.